Hi, can everybody hear me? Great. Welcome, thanks for coming. So this will be a talk about neural networks, a gentle introduction to neural networks. So if you're already working with artificial intelligence and deep learning, this may be slightly repetitive, but let's just see who is in this room actually works on deep learning at this time. Nobody. Perfect. Then you're the perfect audience for this. All right, great. Okay, so my name is Michał Karzyński. I work for Intel in Gdańsk. I'll introduce myself in a minute, but first what this talk will be about. It's going to tell you what neural networks are. It's going to tell you how you can train them and how they learn. And then we're going to go over a number of different neural network architectures that do some pretty amazing things and allow us to do surprisingly well in a number of very difficult tasks. So, like I said, I'm Michał Karzyński. I work for Intel, and in particular, we are working on a product called nGraph, which is Intel's neural network graph compiler. I'll go back to this at the end of the talk, and we can talk about it in the Q&A if you want some more. But this is a product that's being developed in many sites all over the world, but also in Gdańsk in Poland. So this is my introduction to get your imagination running. You remember Lieutenant Commander Data from Star Trek? He had a positronic network brain. I don't know what positrons really do in this brain, but I'm sure the network in his brain was an artificial neural network. And this is the type of network that we're going to be talking about today. So what is a neural network? Well, the best short definition that I've come across is that it's a universal function approximator. So what does that mean? It means that it can approximate any function. It can pretend to be any function you want. So what's a function then? A function in the mathematical sense or the functional programming sense is what I mean here. So that means it's a mapping between an input and an output. If you have an input and you feed it into a function, you're supposed to get the same output from it every time. So it's like building a map. And one example, you can have a famous neural network hello world example is the hot dog or not application, which can tell you if you give it a picture of some food, whether this is a hot dog or not a hot dog. So you can actually, instead of writing some complex computer vision analysis code for this, you can train a neural network to do it, to recognize pictures of food or otherwise from a data set that you created and labeled with the appropriate labels. So what actually goes into a neural network? What are the parts of a neural network? So this is a picture, one of the, it's my version of of the most famous sort of schematic diagram showing a very simple neural network. So in these diagrams, we always show that a neural network has an input layer and an output layer and a number of hidden layers. And these are layers of so-called neurons, which this term comes from the biological inspiration for neural networks on which this idea was based. So each neuron in a network is connected with every neuron or input in the previous layer, and it's connected with every output in the next layer. Each of these connections is represented by a number, which is the weight assigned to this particular connection. There's also another term called the bias term, which is useful for training neural networks, which is always, you can think of it like an input that's always set to 1, which is also connected to every neuron in the next layer. So you have, so in this example, when we want to apply our neural network to pictures, we would represent the picture as the input layer. So, of course, you can take a picture and turn it into a set of numbers. So if for an RGB image, this would be 3 channels of integers from 0 to 255, for example, and that could represent a colored image. So these are just the first 4 values, let's say, of the first color channel, the first 4 pixels of the first color channel. And for a real picture, you would have many, many, many more of these, but that would make the picture too complicated to draw on the screen, so it's just 4 units in this case. And, and that represents our input. Now, this next set of connections, it's called the weights, appear here. We mark them as W. So you have W1 in this case, W2 for the next set of weights, and W3 for the next set of weights. And finally, you have the bias as well. So that's everything these are all the conceptual units of a neural network, or at least a simple feed-forward neural network. So how does it actually work? How does it compute the output of the output answer for the question that you're asking? Well, you go through the neurons one by one and layer by layer. So you start, let's say, with this one. And the calculation you need to make to get the value of this unit is to take a look at all the values from the incoming input. They're all connected to this unit by some weights. So you take each value, multiply it by its appropriate weight, and then sum them all up. So you just sum up the product of the input by its appropriate weight, and then you also add the bias term for this particular example. So then you get the activation value for this particular neuron. Then there's one other thing that you have to do to get the final value of this, and which is to apply an activation function. And this is actually a concept that's also based in biology. In the brain, the neurons that compose our brains don't just pass information from one neuron to the next neuron as it comes in. What happens instead is that there's a chemical buildup of a neurotransmitter in the downstream neuron. So as upstream neurons fire, they release neurotransmitter, which is accumulated in the downstream neuron, and this neuron collects this information, collects this chemical neurotransmitter until it reaches a certain threshold, a certain concentration inside the cell, and then it fires. So this is what these functions mean to represent, which means that at first, when there's some activation of the neuron, nothing happens. But when we pass a certain threshold, when we pass a certain concentration, then the neuron will fire. So these are the functions. Historically, they were smooth functions like the sigmoid function or tanh function were used to represent this threshold. But in later experiments recently, it was found that this simplified function called the rectified linear unit, which is just a simple max of the input and 0. So for any value lower than 0, it's 0. For any value higher than 0, it's the value. Works just as well for training in neural networks. So this is the activation function we use. So we have to apply an activation function to this sum of the weighted inputs and the bias, and that's the value for this particular unit in the next layer. And so we proceed like this, calculating the sum and the activation value for the next unit and the next unit until we have calculated all the activations, all the values for this particular layer. And then we move to the next layer, repeating the process again. And then we move to the next layer, repeating the process again until this is the last layer. So now we have values for these output units. And these are our prediction values. Let's say that this network trained like this will give us a prediction that this picture does indeed represent a hot dog with a high probability, much higher than of being not a hot dog. So that's how neural networks work once they are trained and ready to be used. But how do we actually train them? How do we actually get them to this state? So this first part that I was describing, we often refer to as the inference. So the network is performing inference. But the next part where I want to talk about is the training of the network. So let's go back to our example. And let's say that this network hasn't been trained very well yet. It's giving us some predictions. In fact, when we start, we just set all the weights to random values. There are a couple of schemes how you can set the weights to random values, but essentially they will be just random, so what you will be getting is noise. But let's say that the noise that we're getting is making this type of prediction. So now we ask ourselves the question, what would happen if we took one particular weight in this, whoa, sorry, something is jumping through all my slides. That wasn't me. Okay, so now that we have the prediction, we want to compare it to a ground truth, to the real value. So this is called supervised learning, which means that we actually know what the real answers are, as opposed to unsupervised training, which is also possible to do, where we wouldn't know the answers beforehand. But for supervised training, which is the most popular technique used these days, we have a data set of many, many pictures in this case, and many, many labels. So for each picture, we have the ground truth. Is this a hot dog or not? So if we have the ground truth and we have and the network made a prediction, we can calculate I think my battery died. That's the problem. Okay, I'll be using the keyboard then. Okay, so now that we can calculate, once we have the prediction and the ground truth, we can calculate the loss, which is the cost of this particular network at this time, meaning the error it's making. This is an estimate of the error that it's making. That's the loss function. And we can now ask ourselves, what would happen if we changed one of these weights? And beforehand, the loss that we were getting was 0.6, because we're just calculating the difference between the ground truth and the prediction and summing it up. And now that we're making a change to this particular weight, the loss increases. So adjusting this weight to make it a larger value, to make it a heavier weight, won't help us. So in fact, for this weight, what would happen if we made it lower than it was before? Well, then the loss goes down. So we know that for this particular example, for this particular weight, the good thing to do would be to slightly lower it. And so we can repeat this process over and over for all the weights and all the examples that we have, and this way we will finally train the network to make better and better predictions. And that's really everything that is going on when we're training a network. We're just adjusting the weights. So how do we do this in practice? Well, there's a technique called backpropagation, which is used to calculate the gradients which we're going to be adjusting by, the direction and scale of the adjustment for each weight by using derivatives. And the whole process then of adjusting the weights is called stochastic gradient descent when we're adjusting all the weights. So let me just say a few words about each of these. For backpropagation, the way it works is that we propagate the information forward. So that's in inference. We take the input, we calculate each subsequent layer until we arrive at the final output value. But in backpropagation, we go in the opposite direction. We know the loss, and now we can calculate the derivative of the loss in terms of these weights. So we know how much we need to adjust these specific weights and in which direction we need to adjust these specific weights to decrease the loss, the value of the loss. And once we calculate that value for the adjustment value for this set of weights, we can calculate the next set of values, the adjustment values for the previous layer and the previous layer, and this way we go backwards, calculating each layer in the opposite direction than when we were doing the inference. That's why we call it backpropagation. And this is done by the frameworks that are used for deep learning. You usually don't write these equations yourselves. You usually define the forward propagation graph, and the back propagation graph is calculated for you. But in any case, this allows us to adjust all the weights in a manner consistent with the direction that gets us closer to the network making good predictions. So the next term I mentioned was stochastic gradient descent. So you can imagine that the whole space of all the parameters that these weights define is a multidimensional space. So for each weight, you have a different dimension in which you can move to get a better outcome. So this 3D diagram is just a much simplified representation of this concept. So we just have two parameters that are that we're going to be adjusting, and we want to get all the way to the bottom of this loss function. So the plane represents the shape of the loss function in 3 dimensions. But if you think about it, there's 1 dimension for each weight. But if we think about how the training works in stochastic descent, let's say we start here. We have a pretty high loss initially, but we calculated the gradients for we calculated the gradients needed to adjust the weights, and now we calculate our loss function again. And that will mean that after we adjust the weights, we will be moving down in this plane, in this loss function. So with stochastic gradient descent, we actually make 1 step for a mini batch. A mini batch is part of our data set. So the data set that we have, the set of images that we started with, is divided into small batches. These mini batches are sometimes 32 images, sometimes 128 images, sometimes 256, depending on the software you're using, the size of the images, the amount of RAM that you have available. But you're trying to get a chunk of your data set into the training at once. You calculate the gradients and average them over the data set, or you actually calculate the loss, average that, and then calculate the gradient based off of that. So you don't have to make the calculation for each image, but for a whole batch of images. And so you move 1 step per batch. And then you're here, and you calculate you do the training again for the next batch of images, and if the images are good and the labels are good, you'll be moving in the direction that goes towards lower and lower loss with each step. You may not be taking the shortest route to the smallest value of the loss. You may be meandering a little bit as you go, but with any luck and good data, you will arrive finally at the place where the loss is the lowest, and that represents a well-trained network. So that, in a nutshell, is how we do training. We simply take the training examples that we have, we look at the ground truth, compare it to the predictions that we make. Based on that, we calculate how we adjust the weights, we adjust them, and step by step, we train the network until it's fully trained. And that's actually it. So now I'll move on to the next subject in this talk, which is to talk about a specific neural network architecture called convolutional networks. And now, convolutional networks are usually used with image data, like the pictures that we had, but they work in a very specific and clever way. So let's go back to this picture, because it's a good starting point for seeing what the difference between a basic feed-forward neural network and a convolutional network is. You can think of the convolutional neural network as being a network where one of the layers is substituted by a convolutional layer. So what does that really mean? Well, a convolution operation is an operation which takes the input image, takes a set of weights, which is also represented by a two-dimensional filter, or a filter of the same dimensionality as the input image, and it produces an output image. So how does that work in practice? Well, if we have an input image, hold on one second. So if we have an input image which represents, which is represented here on the bottom as this image of two stripes, that will be a matrix of numbers. So yes, this will be, so this input image, if it's just two stripes, one darker and one lighter, can be represented by a table with numbers. So we have some values like 5s here and 0s here, and we can apply convolution to it using a filter. So this is a filter that comes from traditional computer vision techniques. Something like this can be found in applications like Photoshop or something. This is used to detect vertical images, this type of filter. It's just three stripes also of numbers, and you take each, so you apply the filter by taking by putting it over, like superimposing it over the input image, and then you take each number from the input and multiply it by the corresponding number in the filter. So it's like with the weights, you're multiplying the input by its weight. So for this particular value, this would be the weight. And then you repeat that for each number in the input, multiplying it by each weight and summing that all up. And this way you get an output number in the output image. So if you now move the filter over by 1 pixel, you will make a new calculation and get another value, and you can repeat this over and over and over until you finally get all the numbers in the output, and you create something we refer to as the feature map. So an image representing the map of this feature in this image. And this is how you can detect, with this example, horizontal or vertical edges. And you can have multiple filters, one for detecting horizontal edges, one for representing vertical edges, one for representing sideways edges, and so on. And each of these will create in the output its own feature map. So usually when you're training a neural network, you have quite a few of these filters. But you don't actually put in the filters like you would in a Photoshop application or any application dealing with photographs. These weights are initialized randomly, but then through training, through backpropagation, and through adjusting the weights, filters will be learned. And this is what happens. This is actually a picture from a publication from 2012, the famous AlexNet publication. And these are the filters that the network learned by looking at a large set of images. And you can clearly see that it learned something like the Sobel filter in multiple orientations. So something that detects edges oriented this way, something that detects edges oriented this way, something that detects horizontal edges, another one for detecting vertical edges, and so on and so on. So all of these edge detectors are something that the network figured out on its own, that is something that it will need to analyze images. And aside from these edge detectors, you can also see color boundary detectors are another set of filters that this network learned to recognize. So when you're actually building a modern convolutional network, you don't just have one convolutional layer, but you have quite a few. And this is my favorite convolutional neural network because it's very symmetrical, very elegant. It was created at Oxford, and it won the ImageNet competition at one point. So it starts by looking at an input image. Then it does two layers of convolution of the same size as the input image, but with 64 filters. So there's 64 different features that it will detect in this first convolutional layer. Then another convolution takes the feature map that the previous convolutional layer created and does convolution of that. So it looks for features that are combinations of the features of the previous layer. Now in 64 dimensions, the dimensions of the feature map that was created by the previous layer. Then they do something called max pooling, which is essentially reducing the size of the image by half in each direction. And then they do another set of convolutions on this smaller image, but now with 128 different filters. So they're detecting 128 different features. Then they repeat that, shrink the image down again, and then they make another round of 3 convolutions now with 256 images. And you can see how this progresses until finally they arrive at a very small image, but with 512 different features or ideas recognized. Finally, they shrink it down even further, and they connect every output from this layer with a fully connected layer. So we're going back to the fully connected architecture at the end of this. So now we have 4,096 neurons in a fully connected layer, another fully connected layer, and finally a fully connected layer with 1,000 outputs, corresponding to the 1,000 different classes in the ImageNet challenge. So if this is a picture of a car, then in this final output, the label for a car, the number corresponding with the label car, would have the highest output. And this worked very well, actually winning the competition. And this is what the network learns to see. This is actually an analysis from a different paper of a convolutional network. And this first image here is the same, it contains the same information as the image we talked about before. So these are the filters in the first layer that the neural network learned. We can see the sort of Sobel filters in there and the image transition filters as well. And this next part of the image, for each one of these filters, you can see a part of the image, or you could see a part of the image that most activated this filter. So this is the type of input that gives the highest value for this specific filter. So for this filter, you can see that definitely edges that go across diagonally like this activated the most. For this filter, its edges directed that way, and so on and so on. So for these, so for this last one, you can see a transition between two colors, and also when you have transition between two colors in the picture, that's what activates it the most. That's a green detector, so green patches activated the most, and so on. So that's the first layer. That's the initial layer where the most basic shapes and color transitions are detected. But then we move down. We move down to the deeper layers of the network, which don't look at the input data, the photographic color image data anymore, but now they're looking at the output of the previous layer. So they're looking in more dimensions. They're looking at in the dimensions of all the features that the previous convolution created. And this is a representation of the filters that it detects, and so this and these are the patches that activated most. So in the second layer, you can see that it's no longer just simple edges or color transitions that are being detected, but slightly more complex shapes, like stripy shapes or round shapes, or maybe some corners, or maybe some stripes again. So that's what the second layer is detecting in this paper. And then you go further down into the next layer they analyzed, and you see more and more complex patterns are being detected. So here we see some, clearly some grids. There we already see some, something that is a wheel or a round object that's being detected. And as we go deeper and deeper into these networks, they are beginning to recognize more and more complex features, until finally they are able to detect and distinguish from each other images of a dog, or images of a person, or images of a bird, or a bicycle. So the deeper layers look at more and more complex, they find more and more complex features. So this is a very powerful technique. It allows us to do image recognition, of course, but it's being applied to a whole set of other applications. Facial recognition in your phone works based on this idea. Handwriting recognition, video analysis, even in medicine, there are multiple applications where if you can take some data that's represented by as an image for medical diagnosis, for example, you can then use convolutional neural networks to train it, and with very good success, I might say. So, so our Lieutenant Commander Data was definitely equipped with something like that, probably in his artificial visual cortex. So that's my obligatory data reference again. And now I want to move on to the next architecture. So stepping away from convolutional networks, now going to another very powerful family of networks called the recurrent neural networks. These are used when dealing with sequence data. So let's go back to our picture of a neural network. We have the input layer, the weights, and the outputs, and we can actually simplify this picture a little bit, and that's what I'm doing here, so that instead of having this complex grid of all the weights, we're just representing all the weights by a single arrow here. So this again is the input layer, the next hidden layer, the next hidden layer, and the output layer, and the weights between them. So this simplified diagram will help us when talking about recurrent neural networks. So with recurrent neural networks, we usually draw them like this, with one additional recurrent connection here. So this kind of implies that this creates a loop, and this is what makes these recurrent neural networks. Now this is a little bit hard to reason about, but we can unroll this neural network into something like this. So this connection here is actually this connection in the next picture. So when you're dealing with sequences, you have some input at time t, or step t. Then you have another input at time step t plus 1, another input at time step t plus 2. And how these neural networks work is that you first take the input, go multiply it by all the weights in the first set of weights to get the value for a hidden layer. You multiply that to get the output layer. But you don't only use the output of this layer to calculate the output layer. You also use it in the next time step in combination with the next time step input to calculate this, this particular value for this hidden layer. And then you use that to calculate the output at the next time step, but you also use that. So this now contains information from this time step and also from this time step, so it kind of represents the memory of this neural network. You use that as the input at the next, with the input at the next time step, and to produce the output at the next time step. So you kind of take the inputs as they come in your sequence, but you're also keeping track of the previous values that were in the previous steps of the sequence. This this keeping track is just inputs multiplied by the weights. It's still very simple math, but it represents this idea of memory. So how does this work? Let's say that we have a sequence of letters in a very simple alphabet. Let's say that this alphabet will be represented by 4 possible letters, and each letter will be represented by an array of numbers, with 0 representing that this is not the number, and the 1 representing that this is this particular letter. So this is one hot encoding. So 1 represents this letter. So H is just this this value here. So we take this input and we feed it into our trained recurrent neural network, and we ask it, okay, so what letter would you expect to follow an H? And it says that with some probability after an H we would get an E. So now you have your output at this time step, but you also have memory of this H in the next time step. So when you feed in the next letter, and let's say that indeed this is an E, you ask the network what follows an E, but it knows that it's actually following an H as well. So it's kind of, what's the next letter after HE? And it will say, well, let's say L, and then you can see where I'm going with this. It's going to predict that the next letter for each time step will finally produce the word hello. So if we train a recurrent neural network on some set of words, it will actually, with quite a big probability, remember some of these words and be able to produce them. In fact, when you do this, when you train a recurrent neural network on the entire corpus of Wikipedia, and then you give it one starting letter, and you ask it what the next letter will be, and then you feed that letter into the network and just kind of sample from the network to get some output, you will it will produce something like this. This is an actual experiment that was published by the current director of AI at Tesla about the unreasonable effectiveness of RNN networks. That they actually are quite good at doing this. The only problem with this text is that it doesn't make any sense, but it looks like a proper Wikipedia article with citations and everything. So what other applications can recurrent neural networks be used for? Well, one very useful application is for sentiment analysis. So you can feed in not letters anymore, but let's say words. You can use a technique called word embeddings to represent entire words, and then you can your sequence can be an entire sentence. And when you train a network like this, you can train it to actually judge if a review, let's say for a film on a website, is a positive or a negative review, and it will produce this score. Another quite useful, and I'm sure you've used it yourselves, application of RNNs is machine translation. So this is actually very interesting because you have two parts of the network, an encoder network and a decoder network. And the encoder network takes in the sentence that you type into Google Translate or somewhere, and it uses the same technique of feeding each number until you finally get the values of this hidden layer. And then you use that hidden layer as the input for the decoder network, which will reproduce a sentence in a different language. And a lot of the times they make very good sense. They actually are quite capable of learning, of translating between different languages. But this means that the entire meaning of the sentence is encoded in this set of weights, or this set of activations in this hidden layer. So that's quite amazing to me. Anyway, this is these are RNNs, and they're also very useful for numerous things. So language modeling and machine translation I already spoke about. They're also used in speech recognition. If you've seen the surprising ability of artificial intelligence to produce music or music composition, that's also based on RNNs, which are taught on music as the input sequences. And so any time series prediction RNNs are useful for, and there's also multiple other applications. So if Lieutenant Commander Data played music, and he did, he also composed music, well, probably some form of recurrent neural networks were also involved in that. Okay, so one other thing I want to speak about is higher order networks. You can actually compose these components that we have, these convolutional networks and recurrent networks and other architectures, into higher and higher order structures. So, for example, you can take the combination of convolutional networks and a recurrent network to produce a neural network which does video captioning. So how this works is, you already know how it works. You take an input image, you run it through a convolutional network to produce a set of numbers that represent the output of this network, and you feed that in as the input to your first time step of a recurrent network. And then you take the next frame, or the frame on after some time in the video, and you do the convolutional, run a convolutional network on it to produce another set of numbers, and you feed that in as the next time step of the time series. And when you do this, you will produce the description of this video, which you can then decode into human language. And this is actually how some video captioning experiments are already working. So that's a simple example. But a more exciting example is called generative adversarial networks. Was created by Ian Goodfellow, or the idea was popularized by him, created by him. And this is the architecture of the network. So how does it work? It's composed of two parts again. You have the generator and the discriminator. So the discriminator is really just a simple convolutional neural network, which takes in two input images, and or just one at a time, but it takes in either a real image or a fake image, and produces the output if this is a real or a fake. And at first it doesn't know which ones are real or fakes, but this is supervised learning, so we teach it how to recognize real images from fakes. But at the same time, we're generating these fakes using a different neural network. This one is kind of the inverse of a convolutional network, where you start with some random numbers as input, and then you use a process of kind of opposite of the convolutional neural network to produce an image. And you generate some image which is actually a fake. And because you're training these at the same time, this network is generating images, and this network is learning to discriminate real images from fake images. So as this one is learning to be a better and better discriminator, this one is learning to be a better and better generator. And it's learning how to produce more and more convincing images. And in fact, this works surprisingly well also. So these images come from a site called thispersondoesnotexist.com. You can go there, you can take a look at those. These people never existed. These people were generated by a generative adversarial network trained on human faces. So some of them are very convincing, some less so, but it's still a very interesting technique which can be used to generate not just images, but other things in the future as well. So generative adversarial networks are very interesting. So that's my story about data, and I'm nearly at the end here. One thing I would like to recommend to you, if you're interested in these topics, is to take a look at Coursera. There's a set of courses on deep learning there, which are very good. And if you want to learn more, you can go there. So I will wrap up just by telling you a little bit about the deep learning software that's being used for all this. The popular frameworks are listed here. Most popular are TensorFlow from Google and PyTorch from Facebook. There's another one from Facebook called Caffe, and one from Amazon called MXNet. In fact, there's very many deep learning frameworks, but it seems that these first two are the most popular. Now, Intel also has some software in this space. So ngraph, which I'm working on, is a backend for these frameworks. And OpenVINO is an inference engine which you can deploy in production for making an inference server once you have a trained neural network. So usually a deep learning framework has an architecture sort of similar to this. This is a good approximation of what most of the frameworks have. They have some sort of a user-facing API, which is usually written in Python, and Python is the user interface. But then there are layers deeper in the stack, which are usually written in C++. So because neural networks are used for computation, the input produced by the data scientist or the user is transformed into a computational graph representation, which this computational graph just represents all the mathematical operations that are needed to make the calculation. And this is usually done in this is usually an in-memory representation in C++ objects. And then these get passed into execution backends, which are like graph compilers that are able to execute these computations on different backends, like a CPU, GPU, or maybe a specially dedicated accelerator. And the software that we work on, ngraph, is playing this role of the execution backend. So you can hook it up to multiple frameworks. You can use TensorFlow or MXNet or PaddlePaddle as the input to ngraph, and ngraph then will compile the graph into a different executable for different hardware, for a different hardware platform. If you'd like to find out more about ngraph, you can go to ngraph.ai and follow links from there. So that's it from me. Thank you very much.